Good morning. We introduce an important theorem, the fundamental theorem of arithmetic, in this section. This theorem asserts that every positive integer can be written uniquely as the product of primes in non-decreasing order. Primes have become essential in modern cryptographic systems. Finding large primes is essential in modern cryptography. The length of time required to factor integers into their prime factors is the basis for the strength of some important modern cryptographic systems. We will also study the greatest common divisor of two integers and the least common multiple of two integers. Definition 1. An integer p greater than 1 is called prime if and only if positive factors of p are 1 and p. A positive integer that is greater than 1 is not prime is called composite. Example 1.1. Determine if 7 is prime. Solution. The only integers that divide 7 and 1 are 1 and 7, and by definition 1 and 7 is, by definition 1, 7 is prime. Determine if 9 is prime. 3 divides 9, and therefore 9 is not prime, but composite. Theorem 1, the fundamental theorem of arithmetic. Every positive integer greater than 1 can be written uniquely as a prime or the product of two or more primes, where the prime factors are written in order of non-decreasing size. Example 2.1. Find the prime factorization of 100. Solution. 100 is 2 times 2 times 5 times 5. 2 squared times 5 squared. Example 2.2. Find the prime factorization of 641. It's 641. 641 is prime. Example 2.3. Find the prime factorization of 999. 999 is 3 times 3 times 3 times 37, or 3 cubed times 37. Example 2.4, find the prime factorization of 1024. 1024 is 2 to the 10th. Trial division. Theorem 2. If n is a composite integer, then n has prime divisor less than or equal to the square root of n. Example 3. Show that 101 is prime. Solution. If we can find no prime factors of 101 less than the square root of 101, then 101 is prime. 2 doesn't divide 101, 3 doesn't divide 101, 5 doesn't divide 101, and 7 doesn't divide 101. The next larger prime is 11, and 11 squared is 121, so that's greater than this. 11 is greater than the square root of 101, so we stop at 7. Example 4. Find the prime factorization of 7007. Factors of 7007 must be less than or equal to the square root of 7,783. So 7007 is 7 times 11 times 13. 7 squared times 11 times 13. The sieve of Eratosthenes. Note that the composite integers not exceeding 100 must have prime factors not exceeding 10. Because the only primes less than 10 are 2, 3, 5, and 7, the primes not exceeding 100 are these 4 primes, and those positive integers greater than 1 and not exceeding 100 are divisible by none of 2, 3, 5, or 7. The sieve of Eratosthenes is used to find all primes not exceeding a specific positive integer. For instance, the following procedure is used to find primes not exceeding 10. We begin the list of all integers between 1 and 100. To begin the sieving process, the integers that are divisible by 2 other than 2 are deleted. Because 3 is the first integer greater than 2 that is left, all those integers divisible by 3 other than 3 are deleted. We continue to finding primes and deleting their multiples until we've reached the square root of the maximum value. In this case, the square root of 100 is 10. The remaining integers are provided. So here's our original list, and we have all the numbers between 1 and 100 in rows of 10. So what we're going to do is we're going to remove all the multiples of 2. So we leave 2, And then you can see that every other column is deleted because of the way we've arranged our table. So all multiples of 2 have been removed. Then we move to the next integer that's available to us, and it's 3 and it's prime, and we remove all multiples of 3, and we can see that our table has been diminished. Then we come to 5 and remove all multiples of 5. Finally, what we do is remove multiples of 7, but 7 itself. And so what we have remaining here are all the prime numbers between 1 and 100, including 1, well, 1 isn't prime, 2, 3, 5, 7, 11, 13, 17, 19, 31, and so on. Theorem 3 says that there are infinitely many primes, and since we have to find primes for our cryptographic application, then what we would like to do is we would like to have candidates that are easily found that are prime numbers. So a Mersenne prime has the form 2 to the p minus 1 where p is prime. Not all values of the form 2 to the p minus 1 are prime, but there exists an efficient test known as the Lucas-Lehmer test for determining whether 2 to the p minus 1 is prime. Example, find the first value of the form 2 to the p minus 1 that is not prime. Well, 2 to the p, if I try 2 squared minus 1 is 3. Yes, that's prime. 2 cubed is 8 minus 1 is 7, that's prime. 2 to the 5th, that's 32, minus 1 is 31, that's prime. 2 to the 7th, minus 1 is 127, that is also prime. 2 to the 11th is 2047, 2 to the 11th is 2048, minus 1 is 2047, and that is factored into 23 times 89. Theorem 4, the prime number theorem. The ratio of the number of primes not exceeding x and x divided by the natural logarithm x approaches 1 as x grows without bound. Here, ln x is the natural logarithm of x. We have a discussion on the conjectures about primes, which I'm going to leave to you to read in your text. We continue with the greatest common divisors and the least common multiples. Definition 2. Let a and b be integers, not both 0. The largest integer d, such that d divides a and d divides b, is called the greatest common divisor of a and b. The greatest common divisor of a and b is denoted GCD of a comma b. What is the greatest common divisor of 24 and 36? Well, what I'm going to do is I'm going to take 24 and I'm going to list all of its divisors. 1 divides 24, 2 divides 24, 3 divides 24, 4 divides 24, 6 divides 24, 8 divides 24, 12, and 24 divides 24. And then I'm going to take all of the divisors of 36, 1, 2, 3, 4, 6, 9, 12, 18, and 36. Then I'm going to find the maximum value of both that's on both lists. And so the greatest common divisor of 24 and 36 is 12. Example 11. What is the greatest common divisor of 17 and 22? Well, 17 is prime, so the only divisors it has are 1 and 17. And 22 is not prime, and its divisors are 1, 11, and 22. So the greatest common divisor of 17 and 22 is 1. Definition 3. The integers a and b are relatively prime if their greatest common divisor is 1. Example 12. Are 17 and 22 relatively prime? Yes, because the greatest common divisor of 17 and 22 is 1. Definition 4. The integers a1 through an are pairwise relatively prime if the greatest common divisor of a sub I and a sub j is equal to 1, whenever 1 is less than or equal to I is less than j is less than or equal to n. Example 13.1. Determine whether the integers 10, 17, and 21 are pairwise relatively prime. Well, the divisors of 10 are 1, 2, 5, and 10. The divisors of 17 are 1 and 17. The divisors of 21 are 1, 3, 7, and 21. So trying the first pair, 10 and 17, yes, they are relatively prime. Trying the next pair, 10 and 21, yes, they are relatively prime. And trying the final pair, 17 and 21, yes, they are relatively prime. 13.2, determine whether the integers 10, 19, and 24 are pairwise relatively prime. The divisors of 10 are 1, 2, 5, and 10. The divisor of 19 is 1 and 19. And the divisors of 24 are 1, 2, 3, 4, 6, 8, 12, and 24. So 10 and 19, yes, they're relatively prime. 10 and 24 have a common divisor of 2, so they're not relatively prime. And 19 and 24 are relatively prime. Prime factorization method of finding the greatest common divisor. Find the prime factorization of both integers, identify common factors, common prime factors, identify the minimum exponent common to both factorizations on the common prime factors, find the product of those factors found in step 3. Example, what is the greatest common divisor of 120 and 500? So factoring 120, I get a 2 cubed times 3 times 5. Factoring 500, I get 2 squared times 5 to the cubed. So the common factors are 2 squared and 5. So therefore, the greatest common divisor is 2 squared times 5, or 4 times 5, or 20. Definition 5. The least common multiple of the positive integers a and b is the smallest positive integer that is divisible by both a and b. The least common multiple of a and b is denoted LCM of a, b. So in this case, we have an analog to what we did as the greatest common divisor. So we find the prime factorizations of a and b, and then for every prime in the factorizations of both a and b, we find the largest exponent. The least common multiple is the product of the list generated in step 3. So in example 15, what is the least common multiple of 95,256 and 432? Well, the prime factorization of 95,256 is 2 cubed times 3 to the 5th times 7 squared. And the prime factorization of 500 is 2 to the 4th times 3 cubed. So the maximum factors are for 2, 2 to the 4th, for 3, 3 to the 5th, and for 7, 7 squared. So the least common multiple is 2 to the 4th times 3 to the 5th times 7 squared. Theorem 5, let a and b be positive integers, then the product of a, b is equal to the greatest common divisor of a comma b and the least common multiple of a times b. So we're going to continue this lecture with the discussion of the Euclidean algorithm, but we're going to stop here.